The Schrödinger equation is a very useful relation. It solves many problems for quantum mechanical particles that have mass, such as a single electron moving slowly, that is, much slower than the velocity of light, and when we neglect any magnetic effects. It's also a very good example of quantum mechanics. It exposes many general concepts that keep coming up again and again in quantum mechanics. Ideas such as quantum mechanical amplitudes, ideas such as the underlying linearity of quantum mechanics, and the whole idea of eigenstates. Eigenstates are what put the quantum in quantum mechanics. Why do we even propose an equation like the Schrödinger equation? Well, the simple answer now would be that based on our current knowledge, experimentally, electrons can behave like waves. In the last section, we discussed the idea of diffraction by a periodic array of scatterers. One good example of a periodic array of scatterers is a crystal of some kind. As I said, a crystal is just a regular periodic array of atoms. Periodic means it's got equal spacings. We know that if we shine X-rays at a crystal, as we said, we get diffraction patterns, just as we had discussed. X-rays are electromagnetic waves of very short wavelengths, as we said. The separation of atoms in crystalline solids is something on the scale of angstroms, or tenths of a nanometer. X-ray wavelengths can be this short also, so they can give these diffraction patterns on a phosphorescent screen if we shine X-rays at a crystal. And the specific shape and pattern of the dots on the screen tells us a lot about the structure of the crystal and the spacing of the atoms. But what is also true is that if we shine a beam of electrons at a crystal, we can get a similar kind of pattern on a phosphorescent screen. Experimentally, for example, we can make a beam of electrons by applying a large electric field in a vacuum to pull electrons out of some metal. We have to be somewhat careful to arrange that all of these electrons have essentially the same kinetic energy, so they're all going at the same speed, as it were. And we can do that by accelerating them through some fixed electric potential. So we have our beam of electrons by pulling it out of a metal. If we shine this beam of electrons at a crystal, we will get a diffraction pattern. For example, if we let the scattered electrons land on this same phosphorescent kind of screen, we will get a pattern of dots on the screen. And this pattern of dots is essentially the same kind of thing we got when we shone X-rays at the crystal. And again, we can, at least in principle, correlate these two patterns to deduce the electron wavelength, for example. This kind of behavior and the routine behavior we get every day out of electron microscopes, which are machines that allow us to exploit that short electron wavelength to image structures much smaller than the wavelength of light, these confirm for us that indeed electrons behave as waves. Also, electron diffraction off a crystal surface is a routine technique today in many kinds of modern crystal growth. The diffraction pattern that you get by shining electrons at the surface and seeing them bounce off onto a screen, sometimes called reflection high-energy electron diffraction, or RHEED for short, can tell us, for example, about the quality of the crystal surface that we are growing. Of course, we also know that, at least in some ways, electrons also behave as particles. They certainly have a definite charge, they have a definite mass, and so this fact that we're seeing both wave nature and for sure we know also we have particle nature is an example of what we'd call a wave-particle duality. Anyway, given that we know electrons behave like waves, we need to construct a wave equation. And to construct one, we start with de Broglie's hypothesis relating the electron wavelength to its momentum.